Welcome. We're going to continue with chapter 9. We're going to take combinations and we're going to go up a level. So we're going to start doing combinations, but and when we did combinations before, there was no repetition because once we picked an item, it was done. But what if we now allow repetitions? This is where things get a little bit more dicey and actually becomes a little bit more different. So this idea is a good way to initialize it. We're actually going to categorize the objects and then we're going to pick multiple objects in that area. So if X is, let's say, X1, X2 through Xn, we're going to pick what's called a multiset, meaning I'm going to pick some number of X, let's say X1s, and then I'm going to pick some number of X2s and so forth, where that's possible. I don't have to use X1s and X2s, but I'm just giving an example where I could have, like, let's say I'm picking 5 elements out of 10, where I could take the first element and have 3 of them and two of the second element. That is where this gets a little bit different. And this actually has a lot of really good value and a lot of applications. We will get to those in a little bit. So let's actually do our first example. So let's actually look at the different multisets of size 3 that can be written from 1, 2, 3, and 4. Well, the way to start off to doing this, and in this case, again, order does not matter, but we're going to go ahead and write them in increasing order just to have something to look at and make sure that we have an organized process. But you don't have to write them this way. So multiset, again, no, notice multisets are often written, again, I'm going to come back here notation wise. They are written with a square bracket. That's what your book does. I do know several other books that do some other different versions. We'll go ahead and use this. So a normal set has curly brackets and multi-sets are using square brackets. Okay, so with that in mind, we have 111, 12, 112, 113, 114. These are all the combinations that have a 1, 1, 2 ones. At least 2 ones, I should say. Then let's just go with it has 1, 1 and a 2. So I have 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 2, 4. Those are all the possible combinations. And if I have 1, 3 guaranteed, well, notice I can't do 1, 3, 2 because that's actually the same thing as the 1, 2, 3. Because again, order does not matter. So I can only pick things, and this is why doing this where I'm making it bigger is nice because once I go 1, 3, then my last element has to be 3 or bigger, which allows me to go 3 or 4, and then obviously 1, 4 is the only thing left in that for the ones. But then we repeat the process with 2s, 2, 2, 2, and so forth. We have an interesting thing because here I did all of these and just counting the first several that we already have on the page. We have 4, 3, 3. So just in terms of ones, we had 10 of them right there. And then we have 2 2s, we have 3 more. So we're at 13. But we're not even done. We have to go to another page to show 2, 3, 3, 2, 3, 4, 2, 4, 4. So notice that I kind of lost that this was shorter than this stack. But when I go to the next one, this is almost the same as this stack right here because I just swapped out the 1 for a 2. Okay, so that's kind of a critical part. The reason actually that this stack is identical to this one is, again, I just swapped out the first 1 for a 2, and you get the idea. So we actually have these two things, so we're up to 16, and then we do 3, 3, 3, 3, 3, 4, and 3, 4, 4. Those are all my options because once I have a 3 and I put a 3, the only thing left is a 3 or a 4, and then I have a 3 or 4, well, the only thing left is put a 4, and then a 4, 4. So it turns out there are 20 different combinations. But how do we do this? How do we actually choose our things? Well, one way to do this, there's a lot of ways that we could look at this, but the most common is understanding this idea, and the formula here is r plus n minus 1 over choose r. And your book has this, and it's like, okay, but this really doesn't give an illustration about what's going on. I want you to understand this so it's not just some magical formula, because none of these formulas are magical. So let's go back to that multi-set again. A way to think about it is I have 1, 2, 3. I'm going to pick 3. I'm going to pick 3 things. And again, order doesn't matter. So we might as well say, and then I'm going to have 3 bars or dividers that I'm going to put in. And just for the sake, let's say I put a divider here, I put a divider here, and I put a divider here. Well, everything on this side is going to be ones. Everything in here is going to be twos. Everything inside of here is going to be threes. And everything over here is going to be fours. Now I can move. So does that make sense about, I want you to think about this for a second. I'm breaking them up. Now I could have taken this first bar and I could have obviously just made this first bar go away. And instead I could have even put 2 bars right here, and then the twos are empty, but the ones get 2 ones. So there's all these different options we could have done. So we're just moving around the bars and the stars. Well, this is called the bars and stars strategy. If you want to Google, it's another way to think about this. Well, let's think about it. The reason I have my dividers are 3 is because to break up 4 things, think about it, if I want to break up 4 things, I only need 3 dividers between them because the 2 on the ends just kind of naturally get held off by themselves. So that is actually where you get the n minus 1 comes into play. Now the r is I'm choosing these, so the n minus 1 is the number of dividers because I'm taking 1 less divider than the number of elements that actually I have. This is kind of a critical idea, and this is where this actually gets kind of tricky. Now there's some other applications we can talk about that this problem has tons of applications to. This is a partitioning problem, and it's a very, very classic partitioning idea because we're going to break them up into chunks, and how many different ways can I break up my allotment of resources. So we're going to break them into, we're going to decide how many dividers. I need 3 dividers. If you're dividing something in half, you only need 1 divider to go between the two. So you always need 1 less. So again, that's what the n minus 1. And then the r are the spaces left that I have to fill out. Because the way to think about this is right now, if you look, I really technically have 6 things right here. And then I'm choosing, so I could call them places 1. Right now they're in places 1, 2, 3, 4, 5, and 6. And the way I've currently written it is my dividers or bars are in 1, 4, and 6, where my stars or my spaces are in 2, 3, and 5. I've seen some books call these the divider process method. There's a lot of different names, but the idea is this lets you understand where repetition comes from. Is we're really then allowing ourselves to break these things up. Okay, so let's look at a different example besides just multisets, but it is still multisets. It's just a different real world example. So consider the thing where you have a party and you have 15 cans of soft drinks for your guests. So I want to go get 15 cans. And when I go to the store, there are 5 different kinds of sodas. It says soft drinks. You want to call them, I know here in the South, we call them pops. You can call them whatever you want. We're getting drinks, and I have 5 different kinds of drinks. How many different ways can I choose 15 cans from there? Now realize I could get all 15 cans of the same drink. If my favorite drink is, let's say, root beer, because we're going to use root beer in one of these examples, I could literally get 15 root beers. That's a possible option. Well, to do this, a way to think about that is I am going to essentially have 15 cans. 1, 2, 3, 4, bunch of dots, 15 of them. And then I'm gonna have 4 dividers because I have to break up somewhere in here 5 items. So I'm gonna need dividers, and I'm gonna throw those in. And I'm just gonna say all those before the first divider are type A, all those between the dividers type B, et cetera, et cetera, et cetera. We're going to go through these. So how many ways are there? Well, since we have 15 plus 4 more, that is 19, and we're choosing which 4 of those are dividers, we're going to actually get here 19, choose 4. And we have that answer. So this works really, really nice and beautifully. It's really, really classic, and we can kind of work our way through it and see it. But notice, what if I say that root beer is one of the types of drinks how many different selections include at least 6 cans of root beer? Well, the problem here is now I have at least 6 cans of root beer. So we cheat. If I give root beer 6 cans automatically, so I'm just going to go root beer gets 6. Root beer gets 6. I'm still going to keep my 4 dividers, and root beer could be hanging out in this first spot. I can still add more cans in this area. I don't have to, but I can. And since I've given out 6 cans, I have 9 cans left to figure out where they go in terms of all of this. So I have 4 dividers plus 9 cans. So I have actually 13. And again, I'm choosing the 4 dividers. Now, by the way, you could have said I'm dividing the 9, choosing the 9 cans. It doesn't really matter because remember, one of the identities we've already pointed out before is that the probability that counting something is the same thing as counting what it's not in terms of choosing. Choose what you want is the same thing as choosing how many ways are there to choose what I don't want and then taking the leftover. So that it's still perfectly fine here. All right, so we've done problems A and B. And again, we're simply breaking this down into what do I have left? This makes this a whole lot better than trying to sit there and go, what's this magic formula? Again, if you just look at formulas and you look at this formula right here, and you're like, it's going to get a little bit funky. It's better to break it down and think about these as dividers. And then you can be like, okay, I have this many things I have, and then I'm breaking them into this many groups. Well, how many total things am I counting? How many of those am I choosing? And then you build up that number and you can go from there. So again, last one, the store has only 5 cans of root beer, but at least 15 cans of each type of soda. How many different selections are there? So they only have 5 cans of root beer. Now this one's a little bit tricky because now I have to say, okay, I could take this where I have no cans of soda. I can have 1 can of soda. I can have 2 cans of soda, and I have 3, 4, and 5 cans. We can consider each of those situations where I have 5 cans of root beer. And that is going to, and by the way, the other way to have done this is to have worked through this and said, how many ways are there to do this if I didn't? So I'm going to go ahead and flip to the answer that they have in the slide and show you what it is, that it's pretty much going to be the same idea, but just to kind of show you typed out very nicely. So one of the ways that we're going to do this one, again, the book is reminding us that we can choose at least 5 cans. Well, the opposite of that is we're going to choose 6 or more. So obviously that's a bad situation, but we already counted that number. That was that. Remember, this is when we had going back to number part B, it was where we ended up and we got this answer of 13 choose 4 or 13 choose 9, depending on which answer you want to have. And so with the total number of things, a way to think about this, again, counting, is that my total number is going to be that whole, it's going to be that 19, choose 4, and that's going to be equal to whatever value this is, because that's how many root beer cans, plus if I choose at least 6, which is going to be 13 choose 4. Now, the reason I say this is important is because this number right here is completely disjoint from this. You can't have at least 6 and have less than 6. So because that those two situations are disjoint, but this is the one that we want. And so a classic way to find something, I could have literally been, okay, let's do this. Let's do 0 root beer. All right, so if I get 0 root beer, I essentially, root beer is going to be, I'm just going to give root beer its number. Well, the problem with that is then I lose 1 divider. 1 divider is lost because I might as well just get away. I have root beer and then I have left 19 cans and I'm choosing 3 root beers. That would be 0 root beers. And I could add to that 18, choose 3 if there is 1 root beer, because I would already have given away 1 can, so I'd only have 14 cans left. I still have 3 dividers. So by giving away a root beer, we don't have to pick any more root beers. And then I could have 2 root beers, which would be 17, choose 3, plus now you're starting to see the point that I'm getting at here. We have 3 root beers and we have 4 root beers. And I have to do all this work, and I could do this, and this would still get me the answer, but it's not as beautiful. And that's the point, is that we can sometimes overthink things and actually make them really, really hard for us. So we'd have all these options, and then we have 13, choose 4. Because remember, 13, choose 4 allowed us to go more. It wasn't exactly 6 cans of beer, it was 6 cans or more. That's why that was choose 4 on the bottom. All right, so, but coming back here, all I have to do then to solve this answer is, well, I just have to take my total number of cans and take away the number that I don't want, which is everything over 6, which we've already done. And in this way, I actually get 19, choose 4, minus 13, choose 4, which, if you really want to write that out, that's going to be 19 factorial over 15 factorial times 4 factorial minus 13 factorial over 9 factorial, 4 factorial. Or we can write this as 19 times, I'm just going to write out 18 times 17 times 16 minus 13 times 12 times, what's that, 11 times 10, all that over 4 factorial, which, by the way, 4 factorial is 24. So I can multiply these things out. I can use the compiler strategies that make my numbers a little bit better. Like I can cancel out 24 from each of those groups. And anyways, we can do the calculations in this one. It's not a really big deal, but nonetheless, we end up with this answer, and it has 3,161. Again, I'm not going to require you to do that. If you do that general, more open, that's perfectly fine, especially on the test where you don't have your calculator. Leave it there, be comfortable with it. Computing the actual value is actually not a common thing we do, because we actually usually leave that up to a computational aspect of a computer program. All right. By the way, that's why it's called computer science. In case if you don't know, it's computers, you have to understand the science of how things are computed. It's not coding science. Actually, that's coding theory is a whole different subset of all that. Anyways, let's count triples now. So this is an interesting, this problem becomes a very interesting one. So let's just go through it. N is a positive number with how many triples of integers from 1 to n can be formed, in which the elements of the triple are in an increasing order but not necessarily distinct. In other words, how many triples can I find I, j, k, where 1 is less than or equal to I, which is less than or equal to j, which is less than or equal to k, which is less than or equal to n? This is an interesting problem, because now I want to find 3 numbers that are bounded above, bounded below, but also they come in a specific order. The irony is that I just want to pick the exact situation. So we're going to represent this by a string of vertical bars, and the 3 crosses or stars with the positions of the things I want. So here, notice I can't, because I can't put, how can I phrase this? We're just going to count, because I went to the categories 1, 2, 3, 4. I'm really going to put 3 things into, oh, this one's missing an X right here. And so really I have 3 values I'm picking, and of my n values, I have n minus 1, because I have n minus 1 because I have 1 less than n. So in this case, I have 5, so I have only 4 bars. And so we're actually going to get the whole 3 plus n minus 1, which is n plus 2, choose 3, which is this huge thing, which it turns out is this number. Now, this number may look familiar for some of you, but it actually it does come up at other places. This is actually one of those summation formulas out there. It's really beautiful. It's really cool. I'll leave it there for you to play with. But let's talk about one last example about how we can use these things. And this is where this one is more partition idea than perhaps others. How many ways can I do what's called integer partition? In other words, I'm going to take the number 10 And I want to break it up into the numbers 1, 2, 3, and 4, where those are all non-negative integers, meaning they can be 0 and they can be anything. Obviously, none of them can be 10 because we can't have negative values, so we can't go less. But if one of them is 10, then all the others have to be 0. Well, the truth is, this is exactly still the same idea that we've been doing, because you could essentially take and break it up. And I like this visual right here where you have 10 stars and 3 dividers, where x1 is however many stars are in this spot. X2 is how many ever stars or crosses are in this spot. X3 is here. And X4 is how many stars or crosses are in this box. So this answer of 2, 5, 3 is an answer. And this answer of 4, 6 is an answer. So what we really have is 10 plus 3, choose 10, or 10 plus 3, choose 3. Again, we can choose which one. I usually choose the smaller one, but it doesn't really matter. It's the same exact value. I'm gonna come back here and I'm gonna do one more thing that your video, that the book did not write about, but it is still a valuable thing to ask. What if I change this ever so slightly to say not only that it was equal, but what if I said it was close to being equal? Well, then what? Well, then in reality, it could be that x1 plus x2 plus x3 plus x4, these could equal 10, but they could also equal some remainder. Well, that remainder is between, it could be as little as 0 and as much as 10, because if all of these then add up to 0, then we get here. And the irony is, doing this, adding an extra value right here, I'm still picking the 10 things, right? I'm still picking that 10. But what I'm picking now is 10, and I'm choosing the dividers. Well, I'm doing a divider essentially where the pluses are. And you'll notice I have 4 dividers instead of the 3 from the previous situation. So if you have a less than or equal to, then we have to throw in a remainder, which just modifies it ever so slightly. So you have to be kind of flexible and look at these things and say, what can I do in this ever so subtle situation? And this is why memorizing the formulas doesn't quite work. Play with them and think about them. Think about what we're really doing and why we're choosing. That will give you more power and especially help you apply these into all the different things you might possibly see. Let me know what questions you have, and good luck.